Hi, welcome to my channel, Jabber Time, where I do math videos from algebra to calculus and differential equations. This is my third video for college algebra today, and we just started last week, and the plan is to cover the whole college algebra and calculus 3 within this semester. So far, this is my fifth video today. I recorded 2 for calculus 3 and 2 for college algebra, and this is the third one for college algebra. I have everything written before recording because I want to cover more examples, more material, and take less out of your time recording the video. With all these notes and examples, that takes a lot of time to clean up and write and scan. The recording ends up with clicks with the mouse. It's about 30 minutes and sometimes up to 40 and 45 minutes. So what I'm trying to say is they do take time. They do take a lot of time from me building those videos, but I am committed and I will have them all. I can't promise which day, Tuesday or Thursday, sometimes weekends. The best time is for me weekends, so I could have like some enough sleep, so I could have some relaxing time to make the videos. But just stay with me and you'll have all the videos for all the sections will be covered. Okay, let's get started. We have radicals and rational exponents with examples. This is our topic. The principal square root of a is the non-negative number that, when multiplied by itself, gives you back a. Non-negative is critical here, and just keep that in mind. It is written as a radical expression with a symbol called radical over the term that is called radicand. This is what we mean. This is the radical expression or radical symbol, and the inside part is called radicand. This together is called radical expression, and usually we call it the principal square root. So the principal square root of 25 is 5, and it's not negative 5. What I mean by that, here's something that I want to clear up for you, because sometimes there's chances here and there for some topics that we make mistakes, and this is a chance for mistakes. Everybody agrees that square root of 25 is 5. Check. What I'm trying to say is the square root of 25 is not plus minus 5. If you are thinking plus minus 5, it's because you're thinking that 5 times 5 will take you back to 25, and negative 5 times negative 5 will take you back to 25. If you think that way, it works, but square root of 25 is the principal square root, and it's a non-negative number. You want to keep that in mind. This is exactly what I was talking about. So I'm not going to read it. It's up there. I mentioned that before, and I'll say it again. If you feel like I'm going a little bit fast, it's because I don't want to end up with a video of like over an hour. Secondly, you could pause the video anytime by hitting the space bar, and by hitting the space bar again, it will play. So the space bar acts like a remote control, pause and play. So the principal square root of 25 is written as square root of 25, and it is 5, not plus minus 5. Square root of 100 is 10. It's not plus minus 10. Type this on a calculator as a square root of 100. The calculator will give you 10. It's not going to give you plus minus 10. Square root of the square root of 16 is square root of 4, because the inside part square root of 16 is 4, and we have another square root. It's a 2, and it's not plus minus 2. I keep saying it because It's something that we make mistakes with. Now I can't split the square root here to 25 and 144. It doesn't work this way. You have to work inside, then apply the square root, which is, as you could see, 13. Square root of 49 minus the square root of 81. Those are called perfect squares. Square root of 49 is 7. Square root of 81 is 9. 7 minus 9 is negative 2, and we're done. If you graph y equals square root of x on a calculator, it looks like this. It's a curve in the first quadrant. When you go that far on x-axis, apply the square root, it takes you only up to 5. If you want the negative 5, it has to be a graph underneath in the fourth quadrant. But a function like square root of x is not going to give you 5 and negative 5. That's not a function anymore. Every input has to have exactly one output. That's a function. So this function is different than this function. They're both completely different functions. Try on a calculator, square root of 25, hit the square root, hit the 25, and then press enter. The calculator will give you 5 because that's what you are dealing with. Let's talk about imaginary unit. What we mean by imaginary unit, it's square root of negative 1 is undefined. There is no such thing as a number which is non-negative that you multiply by itself and it will give you negative 1. So when we are stuck with this, we just gave it the letter I as imaginary, and we move on with algebra skills and we solve the problems. So if you square both sides, it's I squared equals negative 1. So the imaginary unit I, this guy here, is the number whose square, when you square it, is negative 1. Now, if b is a positive real number, b is a positive real number with a negative up front, you have to split the square root, and then from there you deal with the square root of negative 1 and the square root of b. The square root of negative 1 will give you the I, which is up here. Sometimes we don't like to write this, because if this is kind of lengthy a little bit or this is too small, you might think this I is underneath the square root next to b. So we kind of sometimes prefer to write the I up front if it's like that with the square root. That's what I meant. Here's an example. B is a positive real number. In this case, b is 25, and b has a negative sign in front of it. 25 has a negative sign in front of it. So you deal with the negative 25 as negative 1 times 25. So I have square root of negative 1. I have square root of 25. That's an I, and that's a 5. So I have I times 5, or for a cleaner look, you call it 5i. Square root of negative 7. 7 is my b for my comment right here, but it's not perfect like the 25. So you just keep it inside. Square root of 7 times I. Now 12 is a little bit different than 25 and 7. That was perfect square. That was not at all. 12, if you break it down, it's a 4 times 3. 4 is perfect and 3 is not. Perfect, by perfect I mean perfect square. Square root of 4, square root of 3. The square root of negative 1 was already done as an I. The square root of, sorry, I went too fast. The square root of 4 is 2. The square root of 3 stays, and I came from the square root of negative 1, so it's 2 square root of 3 times I. That should do it for the slide. Let's do more details about what I was doing right here, splitting the square roots in notes. So if you have square root of a times b, that is square root of a times square root of b. You cannot split the square root if it's not a product. Like, for example, it's a subtraction. If it's an addition, you cannot do that. Square root of 25 minus 9 is not the same as square root of 25 minus square root of 9. Same thing, square root of 25 plus 9 is not equal to square root of 25 plus square root of 9. Let's just check this one. One of them is enough. To do the left hand side, working from inside out, order of operations, 25 and 9 is 34. And that's not perfect square. Using a calculator, it's about 5.8. Here, this is a perfect square, 25. 9 is a perfect square. Square root of 25 is 5. Square root of 9 is 3. 5 and 3 is 8. And that's not the same as 5.8. So just keep that in mind. The square root of AB is the square root of A times the square root of B. But you cannot apply this concept like distribute or how can I say it? Distribute or break down the square root to two parts. You cannot do it when it's subtraction or addition. Only in multiplication and division, because division and multiplication are about the same. Complex numbers. A complex number is of the form a plus bi, where a and b are real numbers. Now when you put I next to b, this right here together in black is called imaginary part. This is called the real part. B is real, a is real, but bi is imaginary part. The complex number system, what is that? It is made of both the real numbers and the imaginary numbers. Do you remember the real numbers from the previous video or 2 videos ago? Real numbers starts with natural numbers, then whole numbers, then integers, then rational, then irrational. All these are something that we could point to and refer to on the number line, the real number line system. Adding to them the imaginary numbers, combined, we get the complex numbers. Let me clear this as a graph. So in general, if you consider a plus bi, if this is gone, if it's cancelled, if b is 0, you only have a. That's real numbers, fractions, decimals, repeating decimal, non-repeating decimals, all kind of stuff of real numbers. But if b is not 0, that means it stays with you. You have bi, you do. That creates another set. It's called imaginary numbers. The real numbers, the imaginary numbers that we imagine together gives us a system that's called the complex numbers. Using the product rule to simplify, square root of 100 is 10. Square root of 300, because 300 could be looked at as 100 times 3. I could take advantage of knowing this and write here 10 square root of 3, and we're done. Now you could think about 300 as, let's say, 150 times 2, and you could try some other ways. But with skills and practice, you could see things quicker and faster. That's why I'm trying to expose to you as much as I can examples, and I'm rewriting everything before I record to one more time to save you some time. It's already about 15 minutes so far, and I'm almost like 1/3 of my slides, 1/3 of the way. Square root of 162, a to the power 5, b to the 4th. 162 is 81 times 2. 81 is perfect square. a to the 5th is 1, 2, 3, 4, 5. Now you don't have to write it this way, but that's my first example with too many letters inside. So that's a process how you want to think and break it down. b to the 4 is 1, 2, 3, 4. That's the square root of 81. That's the square root of 2. These two together will be handled because it's a square root. It's nice to have it a square together under the square root, which gives you absolute value of a. We talked about this early in this video when I used the absolute value. This right here gives you another absolute value. This right here stays. This gives you absolute value. This gives you absolute value, b squared. But when you multiply these two, that's going to be the absolute value of b to the second, which you don't need the absolute value anymore, having the second as an exponent, because the exponent as a second will handle a negative sign if it appears. So I don't need the absolute value anymore. 9. Absolute value of a, absolute value of a, that will give you a squared. Absolute value of b, absolute value of b will give you b squared. This is a square root. This is a square root. And they stay together, combining them. Square root of 2 times square root of a, which is square root of 2a. Hopefully that was clear. It's a little bit fast, but as you can see, it's too many pieces. The square root of the product is equal to the product of the square root. The square root of a times b is the same thing as the square root of a times the square root of b. We have a similar one to the quotient, and looks like this. Square root of a over b is the same thing as the square root of a divided by the square root of b. So in other words, you could split the square root in the product and the quotient, but of course not for the subtraction or addition. Using the product rule to simplify the product of multiple square roots. Let's take a look at some examples. In this case, square root of 12 times square root of 3, it's written as two parts. I want to take it back to one part. So I could take it part to square root of 12 times 3. The reason why, because that's a nice looking number under the square root. It's called perfect square, which is 36 in this case. Square root of 36 is 6. Done. So I use the product, but backwards, to take it from two parts to one part only. Let's take another example. Let's put this everything together. I could see that 50 and 2 will make 100. That's 100. X times x is x to the second. Square root of 100, square root of x to the second. This should be, on the safe side, absolute value of x. It's not actually true to write 10x because there is nothing right here giving to me that x is a positive number. So I have to be careful. Well, you know what? I take it back. Why I'm not writing the absolute value of x here? Because actually this part by itself is a real number, positive or non-negative, unless if we're dealing with imaginary numbers. And this right here is also square root of x, where x is a positive number. So probably that's why. But overall, in case, it would be nice if you write the square root. You don't have to do this one because it came already from parts, not from a square root of x squared. We made this was not part of the problem or given to me. That's why. Let's take more examples. This time I'm talking about radicals instead of product like the previous slide. You could split this square root of 5 over square root of 36. Square root of 36 is 6, but square root of 5 stays. So that's pretty much it. We're done. 2 square roots. We'll take it back now to one square root. One big square root with a fraction inside. As you could see. Y cancels. X to the 11 over x to the 7. subtract 11 minus 7. That's a 4. 234 divided by 26 is a 9. Split this now to two pieces. Square root of 9 is 3. Square root of x to the 4 is x to the second. And we're done. This is what I said early, and I have to make it clear enough. That's why I'm doing it this way. Kind of like standing out or highlighted. Square root of 5 to the second is square root of 25, which everybody agrees it's 5. Square root of negative 5 to the second is actually square root of 25. Working from inside out, the negative 5 being squared is also 25, so both will give you 5. What does that mean? If a here, positive or negative, it doesn't matter. The square will take care of the negative, and you're going to end up with a, the positive number. Your principal square root is a non-negative number. But the original number, because of the square, you don't know if there was a negative, because down the road it was cancelled. So you can't write square root of a squared being a, because a could be negative like this case, that you have to get rid of the negative, which means the absolute value. That's one way to say it. So in this case, a is 5. In this case, a is negative 5. Absolute value of 5 is 5. So it didn't do much. Absolute value of negative 5, that's my a now, is 5. So you want your answer to be positive. You don't know if the original was negative. Apply the absolute value to it, and you'll be fine. Absolute value of b to the 4. If you take your time and simplify it, you don't need an absolute value, because it's like two pieces of b to the second, which gives you absolute value of b. But square it, the square will take care of the negative. You don't need both the absolute value to keep it, because absolute value means if your answer is negative, you have to change it to positive. But I'm already squaring that, so the square will handle the negative sign. So you don't need the absolute value here, since this is on the way. Just b squared. So what this summarizes is, or in short, it's the following. Square root of b to the 4 is b to the second. You don't need an absolute value. Let's take some examples. 20 square root of 72 a to the third b to the 4c minus 14 square root of 8 a to the third b to the 4c. It looks like we have a lot in common. Kind of lengthy. To stay focused with you, I took the time to write this right here on this side, this right here on this side. Then once we're done, I'll get back to the problem. So let's take this part right here. It's kind of lengthy to write while I'm recording, so I'm taking my time writing all my notes before recording to save you some time, and you could slow me down by hitting the space bar, as I always say. Let's take a look. 20 outside, 72 is 9 times 4 times 2, or 9 times 6, 9 times 8, I'm sorry. And we have a 9 as a perfect square, 4 as a perfect square, 2 has to stay inside. A to the third is a to the second and 1a. B to the 4 is b to the second. C is a loner, stays by itself. That's a 3. That's a 2. That stays, that stays, that stays. So what stays inside square roots are the 2 and the a and the c. Square root of 2ac. That is a b square. That is an absolute value of a. And 20 times 3, 60 times 2, 120. We're done with this part. Let's go to the second part. Same process, same style. I have 8 as 4 times 2. 8 to the third, same thing. It's a to the third, b to the 4c, same process. All right. That stays, that stays, that stays, as you could see. Square root of 4 is 2. 14 is right here. And we're pretty much done with this one here. And now 14 times 2 is 28. Subtract this minus this, because that's the problem. I would be subtracting 120 times, as you can see right here, minus 28 times next to it. 120 minus 28 is 92, and this is the same like this. That's why I could combine them in one term. We're done. Here's another topic: rationalizing a denominator containing a single term. Why do you have this in math? Because we could handle and deal with 1/2. Nobody has a problem dealing with 1/2 and pointing to it on the number line. But what about if it's 1 over square root of 2? We don't like square root of 2 to be a denominator. That's a rational number. It's kind of hard to point to that on the number line. So we rationalize, make it rational, the denominator. How do you do that? Here's some practice. Square root of 10 is irrational, and it's in the denominator. To get rid of it, we're gonna bring in another square root of 10. So next to it, multiply by square root of 10 over square root of 10. This part right here and this part right here will make it square root of 10 being squared. No more square root of 10. So that's a 10. That's a 3 up front. 3 times 10 is 30. And this right here, if you take it back to one piece of square root, it's square root of 30 times 2. Between 2 and 30, divide by 2, 1. Divide by 2, 15. Final answer, square root of 30 over 15. Let's take another one, but this time with not single term, with 2 terms. What do I mean by 2 terms? I have the following. Here's an example. 1 plus square root of 5 in the denominator is a complex number. No, sorry. Irrational, but has 2 terms. There's no complex here. How do you handle this to make that square root of 5 goes away? To do that, I want to give you some introduction on the right side. Then I'll get back to the problem. So give me like a minute. We know in math that a squared minus b squared gets factored to a minus b times a plus b. It's called the difference between two squares. With numbers, if a is 5 and b is 2, I could read this as 5 to the second minus 2 to the second. So a is 5, a is 5, b is 2, b is 2. So this one here is 5 minus 2, and this one here is 5 plus 2. If I do the math to see if this works with numbers, the left hand side is 5 minus 2, which is 3, 5 plus 2, which is 7, 3 times 7 is 21, 5 squared on the right side is 25, 2 squared is 4, 25 minus 4 is also 21. Just to support that this formula works, we'll now use numbers like this instead of 5 and 2. So one of them has to be a plus. It doesn't have to be like the second one. And one has a minus with the same a's and b's. Here's a plus, here's a minus. This is the same number, call it a. This is the same number right here, let's call it b. Applying this method, I'm gonna square a. I'm gonna take minus, or take the difference, and take the square root of 5 and square it. That's my b. This part right here is 1 minus this will take care of this and will give you 5. 1 minus 5 is negative 4. Okay, I think we're ready for the problem. So we bring this. Why? Because look at the denominator. If I have a plus b, I bring a minus b. I have the left hand side. So I could jump in to something like that, squaring the square roots, no more square roots. That's how we get rid of the square root when you have some part like this or like this. The denominator, when you multiply across, it's already done for you right here. That's a negative 4. If you do the distributive on top, you get 4 minus 4 times square root of 5. But look at the 4s. It's all over the place. I could make it clear to factor by factoring 4 out first. I don't have to, but that's an option. Or when you multiply here, you could just keep it outside to cancel the negative 4 if you pay attention to the negative 4 coming down the road. So I end up with negative 1 here somehow, because I do have a negative. Could be on top, could be the bottom side, it doesn't matter. Simplifying this, I have 1 minus square root of 5 over negative 1. Or, differently, that becomes positive when you divide, that becomes negative when you divide. So it's square root of 5 minus 1. Now let's talk about rational exponents. A to the power m over n could be written two different ways. You could split the m over n to m times 1 over n or 1 over n times m. Either way, I mean, you could go m times or 1 over n times. So if you want to take care of the 1/nth first, which is nth root, and m outside as a power m, or you could handle the m inside first, then apply the nth root after. This is a little bit dry for now, and if you feel like I'm going too fast, I have some numbers right here and I'll explain it to you. Square root of a is a to the power 1/2. Square root of 100 is 100 to the power 1/2, which is 10. Cubic root of 125 is 125 to the power 1/3, which is 5. All what I'm trying to say here is, when you see 1/3, 1/2, that's like the 1 over n here. So if n is 2, we're actually looking at square root. If n is 3, we're looking at 1/3, which is cubic root. Sometimes students, they ask questions like, I can't find the cubic root on the calculator. I go like, if you can't find it, you could try it some other way by typing to the power 1/3. You could test it yourself. I'll give you a quick example. 2 times 2 times 2 is 8. Cubic root of 8, to practice on the calculator, it should give you 2. So if you're doing it right and you get the answer 2, that means you are doing the right thing. So on your calculator, you could test it 8 to the power 1/3 as a cubic root. If it gives you 2, that means you're doing it the right way. So you don't have to look for the nth or the cubic root. Imagine if you need the 5th root. They're not going to have a key for every single root on the calculator. So it's good to know the other format of typing 1/3 or cubic root, 5th root, 1/5, and so on. Here's another example. Since we have m over n, this time I'm gonna have both. So in this case, 2 is like my m and 3 is like my n. 125 to the power 2/3. I could take the 1/3 first inside, keep the 2 outside, and that's this part right here. And the cubic root, this means cubic root, we just talked about that, of 125, which is 5. After that, square it, answer is 25. Let's do a different fraction, not 2/3, this time 3 over 2. Well, because this is perfect square, I'm gonna take the half first in. I mean, I can't have every single example here to show you different techniques, but it takes some time and practice to see things quick. 100 with the 1/2 on top of it works fine. So I'm going to take it inside, leave the 3 at the end. Square root of 100 is 10. To the third is 1000. And that should do it. Let's simplify rational exponents. I have 5 times 2 times x to the power 3/4 times 3 times x to the power 1/5. I'm using black here to underline the 5 and the 2 and the 3. I'm using blue to underline x to the power 3/4 and x to the power 1/5. So we want to stay focused. So if you multiply the numbers, you get 5 times 2, 10 times 3, you get 30. Put the x's next to each other. This acts like x to the power m times x to the power n. So you need to add m and n. To add 3/4 and 1/5, I need a common denominator, which is 20. And to add those fractions, I know how to add them quick. It's going to be 20 and 15 plus 4, which is 19. That should do it for this. I have, as you can see, another space for another problem, because on my notes, I don't like to write all over the place. We end up sometimes rushing in classrooms on whiteboard, and we end up writing on the sides and the corners because it's different. Time is limited and we need to cover enough material. So with the videos online, I'm taking my time and seeing how much it's gonna fit. And if it's a lengthy problem, all what I do, I start up left, minimize my font such that it's gonna go all the way here and not gonna go over another slide. Because at least in my point of view, I don't like to see a problem halfway I end up with a different slide to move on, then I forget the first half, or I'll have to go back and forth to see what was given. I like to keep everything on one slide, so when I finish, I could stare at the whole thing at once, go back and forth, and make enough connections between what was given, how did we approach it, and how what was the final answer. Okay, let's take care of this example right here. This time I have 9 over 16 to the power half. This half means square root. So one big square root. You can see that. I'm going to split the square root to 9 and 16. Why is that? Because 9 is perfect square. 16 is perfect square. They work nicely when you see a square root. As you can see, 3 over 4. And that should do it. Hopefully I was not going too fast. This is my 5th video today. It took me the week between classes, sometimes before sleeping, in the morning, writing notes for those videos. So finally I came up with those 5 videos. 2 for Calculus 3 and 3 for college algebra. That's 1 week preparation, and I finally made it. Within a week I'm gonna have another 5 or 6 or 7. It depends on how much free time I could have to build those notes and record. Okay. One of the videos I ended up recording 3 times for some reason. Sometimes the program freezes on me and things happen. So it's kind of hard to promise you every single Tuesday, as I always say, but I will keep going on. And I am so excited to deliver all my math experience and knowledge to my channel and my playlists. So stay with me, and within a year or 2 you're gonna see enough videos. For the last 4 months I do have, like, I think over 50 videos uploaded already. Calculus 1 was covered 2 weeks ago. Now this semester I'm covering college algebra and Calculus 3 besides some other topics that I get for my high school and my college. So stay with me and you'll see more and more and more coming. Thank you, and I'll see you next time. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.